receive antenna are the same. So converting the receiving aperture into the gain, we have find that what are the interrelationship, etc., etc. So now the thing is how it will detect the signals. Okay, because already in the signals or by means of signals we mean the echo signal, because what the radar transmit, that thing is known to us, and what the echo the radar will receive, that is actually of main important. And by comparing these two signals, we can extract any other information for the existence of the unknowns or the intruders like this. So actually, when we will define that what kind of signal is there, what are the nature of the reflection coefficient or the scattering cross section parameter, then that entire thing is becomes very complicated. So why it becomes complicated? Just let us go back to the previous pages. So there we can see the kind of things like this. Uh, this graph, because just to, if we follow this graph, that with the time, here we have plot the power, and in the there are two levels, one is the RMS noise power level, another is the threshold levels. And this arbitrary trace what we have plot here, that is the receive depot. Okay, so the basic or the fundamental is, if this echo or the process signals that is above the threshold, then it will indicate the presence of some unknown parameters or the unknown things. If it is below this, then it is indicating that there is nothing, no changes in the background. It is the entirely responsible from the background scatterings or the background reflections like these things. But sometimes this may happen that the component of the echo signal which is coming from a really appearing object, that becomes so small that sometimes it becomes totally masked by the noise levels, or by the, I mean by the clutter signals. Clutter means the background, all the fixed members who are present in the background. So sometimes it may be covered by them. So then it becomes very tough that how do we detect that very weak or very faint echo signal which is really coming from a new object or the new intruder like these things. So if we consider the total things, that means the detection of the actual signal out of the total trace of the clutter or whatever you call it as a noise, it is limited by the receiver's functions, it is limited by the threshold detections, it is limited by the statistical nature, it is also limited by the fluctuations of the background, because these things also we have considered that suppose because of some changes or because of some ambience factor, the entire environment becomes I mean it's very disturbing. So because of some wind velocities are there, some rainfalls are there, so because of all these atmospheric changes, sometimes we get some special existence or some extra echo from the clutter itself, actually which is not signal, this is purely disturbance from the clutter. So that things also we have to exclude. Sometimes this may happen that in the same resolution cell, a very weak signal is there, which is really coming from a newly appearing object, and the disturbance of clutter is there. So there we need more number of resolution cell or more number of distribution, so that we can becomes very much distinctive about the presence of the newly object with respect to the clutter disturbances or the kinds of things. So these kind of fluctuations or the uncertainties, they are very common for the radar operations. Even the other losses, I mean the system losses, the propagation losses, the free space losses, all these things are very much obvious there. So considering all these things, there are two very big issues, that things I will consider here. That thing is false alarm probability and missed detection. These two are two simultaneous events. Simultaneous event. Why these two are simultaneous event? Just if we go back to that previous curve, then the thing is, then the thing is that if we make this VT to a lower level so that the total system becomes very much conscious about the presence of the weak echo. Then what will happen? That the fluctuations of the noise or fluctuations of the clutter that sometimes or often will exceed the level of the threshold, and often it will lead us that something is appearing there or some newly object is there. Okay, so this probability is known as the false alarm probability, because this is very clear that when the trace of the signal will exceed the VT level, that indicates the existence of some extra energy. And what is the source of that extra energy? Source of that extra energy is with the clutter or with the background, some extra component of scattering cross section is there, and because of that things, this extra excursion is there. So that is the normal expectation or the normal phenomena. Okay, so if we make VT lower to catch the weaker echo or the weaker kind of target signals, then what happens? Often it is mislead us by exceeding the level of the VT. So this is a kind of problem which is known as a false alarm probability. And its simultaneous effect, suppose to stop that things, that means to stop the probability of the, or to make the probability of the false alarm lower, what we can do, we can make VT to a sufficient level. That means the threshold. So then what will happen if there is a really object and it is giving a very small scattering, or the contribution of the target is giving a very small scattering cross section? I means the sigma value becomes very small. We have already seen the existence of the sigma value, that is in these equations. This sigma by 4 pi r square is the re-radiated power. So this sigma is the responsible scattering cross section. That means from where all the echoes are generated, this sigma is actually contributing the sum of all those cross sections. So within this sigma value, actually the background clutter cross sections are there, plus the object cross sections, that means what I want to detect or what I want to range, that thing is also present here. So from the sigma value, we have to exclude the actual object portions, and we have to reject the other clutter. So this sigma, that means for which we are getting the scattering cross section. So within this, the echo is there, the real object echo is there, but because of the higher level of the VT, it becomes to the lower range of the VT. That means it is not able to exceed the level of the VT. So that problem is the misdetection. So these two are very simultaneous. That is, whether if we lower VT, then we are led by the false alarm probability. If we make VT higher, then we are led by the misdetection probability. Okay, and the entire thing is very much statistical one, because no one can say that what will be the ambience, what will be the atmospheric changes, what are the changes behind there, what are the things, etc., etc., and what will be the even the system performances. In the case of satellite, there also we have considered the system performances, because when we process the signal across the several subdivision, the performance of the systems over the microwave signals, that also gives some noise contributions or the thermal noise. So including all these features, we cannot make the level of the VT or the RMS level to a fixed one. That is a very much statistical one, and based on the situations or the ambience, we may change all those values. Okay, so let us come to the calculations. So if I write the range equation in terms of the noise figure, you know the definition of the noise figure or the kind of things in terms of the output noise and the input noise. So if I write that one, because that things first we will lead us to calculate the minimum S by N, isn't it? So noise figure, if I write it, this is in terms of Fn, then Fn is equal to how much? Output and by N input at 290K, because that is the standard temperature, or that is known as the physical temperature, what we show with the symbols in terms of T naught. So if I just write it, then NO, this is an input noise means the system noise, that is KTB into G. Okay. Because at microwaves we know K is the Boltzmann constant, T is the thermal noise temperature. That things here as it is we are making it at T0. So K T0 B into G. Why we are considering this is at T0? Because usually this T is the system noise temperature. So we have to write this is KTB, and to make the contribution lower, what we can maintain this at the physical temperature or the ambience temperature at 290 degree Kelvin by using the cooling systems. So that is why we are considering that if we maintain the cooling system, then the minimum possible temperature, that temperature is T naught. So K T naught B into G, where G is the available gain of the systems. Okay. So if just we write these entire things, then can we write the things that is Fn is equal to, because this G is how much? This G is the system gain. So G, what we can write for G? G can be written as S out by S in, isn't it? S out by S in. So just if I replace G factor with the help of the S out by S in, that means output signal by the input signal, then can we write for this F in as this S in will be in the numerator. So S in, this KTBG, that will be the N input. So that can be written as totally in the numerator. And S out is already in the denominator. So S out, and N out was in the numerator. So we can write it is in form of like. So the thing is, noise figure of thing is S input, S by N input, that is S by N input by S by N output. Okay. So S in, that is the input signals, that is equal to how much? That we can write as K T0 B Fn S out by N out. Okay. So these things we can write, and this S out by N out, that can be considered as minimum available S by N at the radar receiver. So here the range equation, if we substitute this value of S min, if we substitute this S input in the equation of the S min, then this thing is R4 is equal to how much? R4 is equal to PT G AE sigma. These are the numerator component, and in the denominator thing is 4 pi square K T0. Here it was S min. So instead of S min, let us substitute these things. So the thing is K T0 B F, rather Fn it is, noise figure, Fn S by N output. Okay. Or we can consider this is as S by N minimum. So that this one is range bands. Okay. So this minimum detectable signals, what we have substituted here in terms of the S by N minimum. So that is the dependency of the entire things with respect to your range. Now let us come directly to the misdetections and the false alarm probability. So for the false alarm probability, let us take as subsections of the radar receivers, because if we start from the IF amplifier stages, then this is the IF amplifier stages. That means including amplifier and the filter both simultaneously. Then the second detector, already I told you that second detector may be an amplitude detector or it may be a phase detector, based on that whether we are just trying to find out only the trace of the echo signal or both trace and phase of the echo signal. That means whether we are only considered to conclude that the amplitude trace or amplitude plus phase, because some MTI kind of applications or the pulse Doppler kind of applications, their phase information is also needed to find the Doppler frequency or the Doppler shift values. So let us just here consider this is as a second detector only. We are not specifically telling that whether it is amplitude or the kind of things. Right now, let us start as amplitude detector itself. This is the video amplifier and the threshold detector. So let us just consider these subsections. Okay, that means after descaling the input signals or after descaling the received signals one scale down, then whatever the changes we are considering or whatever the processing we are considering, that things let us consider here. Okay, so when we are considering all those things, already I told you the entire thing is very much probabilistic one. So there, if we consider this and suppose the envelope of the things or the voltage amplitudes, what we are processing here, that amplitude we are showing with the factor R, then can we write the things for the receiver noise itself? Because what is the problem of the false alarm? The problem of the false alarm is when there is no real signal, only the fluctuations of the noise that is creating the exceeding of the threshold. That is the problem of the false alarm. Clear? What is the problem of the false alarm? That when the fluctuation of the noise that becomes so high that it is exceeding the level of the VT. Actually, there is no other echo signals or no other extra component from the desired target or from the real object. When this happens, then we are led by the false alarm probability. Okay, so this happens because of the fluctuations of the clutter signals itself or because of the fluctuations of the noise itself. So when we process the entire thing to the data receiver, suppose R is the envelope, what we have detect through these stages, that is the IF amplifier stages, the second detector, and through the video amplifier. And obviously, as it is coming from the noise itself, so the processing of the entire things that we have to consider in terms of some probability. Okay, so when we consider this is in terms of some probability, so suppose P function of V, that is giving us the probability of finding the noise voltage, probability of finding the noise voltage between the range V and V plus dV. Okay, and usually we profile the noise signal in terms of the Gaussian, because Gaussian profile is a very uniform profile and it has a bell shape form like this. So just if I apply the probability density function, which is applicable for the noise only, with the R as the envelope, then instead of V, we should substitute the factor with R, because here with the help of R notation, we have shown the excursions of the voltage. So we can write this is P of R is equal to R by psi naught exponential minus R square by 2 psi naught. So just checking the things, these functions what we are writing, that probability density functions PDF. That PDF is a Gaussian profile, and here we have written this in terms of P of R. Okay, so where what are the parameter? The psi is the root mean square noise voltage, and R is the envelope of the things. Okay, so now what is when we are led with the false alarm probability? When the R value will exceed the VT level. So just if we integrate the total thing to get the probability, because this function is probability density function, so to get the probability, what we have to do, we have to integrate it over the total range. So what is the total range? Total range is when Vt is less than R, less than infinity, isn't it? Because just if we go back to that curve, the thing is, if this exceed Vt, so lower level is Vt, upper expression may go up to the infinite value.
ম্যাম সাইন নটটা কি?
Sin of the root mean square value of the noise. দেখো জিনিসটা কি হয়েছে, এই সিগন্যালটাকে আমরা এখানে প্রসেস করছি তো আফটার দিস, তো সিগন্যালটাকে আমরা আর দিয়ে দেখাচ্ছি। এবার প্রবলেমটা কি, আমরা আর দিয়ে সিগন্যালটা যেটা বলছি সেই আরটা টোটাল সোর্সই হয়তো ক্লাটার, এর মধ্যে কোনো সিগন্যাল কম্পোনেন্ট নেই। তো টোটাল সোর্সই যখন ক্লাটার, তার ফ্লাকচুয়েশনের জন্য যখন আমরা এক্সিডিং অফ ভিটি লেভেল, when we are getting the exceeding of the VT level, তখন আমরা we are trying to find out যে what is the probability of this event. J R is totally responsible, or R is totally getting from the clutter fluctuations or the background fluctuation. Let us recall at the, as the background fluctuation. The background is some fluctuations, some turbulence are there. Because of that things, we are getting some extra excursions and it is exceeding the level of the VT. So that is actually the case of false alarm. So now we have to find that what is the probability of happening this, because if we are not able to justify our receiver that what is the kind of probability of giving us false alarm, we will not be able to establish the theory of the detections. Okay, so to find these things, these calculations we are doing. So for this, what is the basic thing? Basic thing is, first we have to give, as it is only the covered by the noise itself, so we have to take some probability density function to describe that noise function or clutter function. So for this, we have take the Gaussian profile. So inside the Gaussian profile, that means for PV here we are writing PR. R is nothing, just to replace V, we are writing R. So V by psi naught, these things exponential minus V square by 2 psi naught. Where psi naught is the root mean square noise level. Okay. Because in the graph we have shown two level. The lower dotted level, what is that? That is the root mean square noise level. VT is the threshold. VT will be decided by the radar operators or by that those kind of people. So that is the things here. So now to get the probability, we have to integrate the probability density functions. So what is the range of the integration? The range of the integration is lower limit is Vt, upper limit is infinite. So if I do that, then what is the thing? The thing is integration Vt to infinite. We have to integrate this whole one, that is P of R into dr. Okay, so when we do this, then Vt tends to infinite. R by, let us substitute the expression of this probability density function, R by psi naught exponential minus R square by 2 psi naught into dr. Okay, so if I integrate this one, what is the result? What is the result of this? This is only exponential minus R square by psi naught. This thing will be valid. So when we substitute the lower limit, then these things will be, R will be replaced by Vt square by 2 psi naught. This one. Okay. So after substitution of the limit, we get the entire thing. This one is Vt. We get the entire thing in terms of this. Okay. So this is the probability of the false alarm. This is the probability of false alarm, because these integrations or this R part is totally from the clutter itself. No extra object is there, nothing is there. So the thing is, just if we have a very close look over this, let us indicate this is as suffix PFA. FA stands for false alarm. So this is equal to like this, and this is totally dependent on the ratio of the VT by 2 psi naught. What is VT? VT is the threshold voltage, and psi naught is the root mean square noise level of that Gaussian profile what we have picked here. Okay, so that is the kind of things what we are considering here. So now the thing is, actually, if I consider these things, then the thing is that with the probability or with these expressions, we are, or the operator is not becomes very strong by consideration of the for the consideration of the false alarm, because probability is just giving us a measurement. It gives a ratio to this, but instead of probability, if we are able to express it in terms of the time factor, that means at what gap the buzzer will be there, or at what are the gap between the getting the false alarm, that is, I think, or the most better way to get the measurement for this false alarm, isn't it? So let us measure the time between, or let us express the entire thing in terms of the time scale. That means let us measure that what is the time gap between the false alarm. That means when only the noise signal is exceeding the level of the VT, what is the time gap between these two happenings, or between these two events? I think that will be the most better way to express this one. Okay. So let us consider that time between the false alarm or the measurement of that things. So we can write that things, that is the average time average time between the crossings of the decision threshold. Let us indicate with the as the false alarm time. So that is nothing but the false alarm time. So what we how we can represent it is, we can represent limit say n tend to infinity 1 by n summation over k is equal to 1 to n tk. So to get the reference of these things, let us follow this time map. So this is your time scale and this is your envelope of noise voltage. Envelope of noise voltage. These things, this is your level of root psi. This is your root psi level. This is suppose your decision threshold, Vt. Decision threshold. Let us take arbitrary fluctuations of the noise voltage itself. Okay. Suppose these are the things. Okay. So what is your Tk? Here the first positions when the profile of the noise signal exceed the decision threshold. So this is the indicating of the first event. Then again here it has crossed the decision threshold. So gap between these two is your Tk. Okay. Again, just if we follow the things, and when we are studying these things, there is no real signals. That means no object is appearing. Just for the background clutter or the background movement, we are taking the data and we are following the processing of the things. So this is only for the noise itself. Okay. And although the it is only we are receiving the signal only for the noise itself, but the fluctuations of the noise, this leads us the exceeding of the decision threshold, and this is the graph. So where TK is like these things, and let us indicate that how long this fluctuation that remains above the VT level. Suppose we are indicating that with this small TK. Okay. So similarly, again, it is appearing here. So this is indicating with small tk. So two kind of time parameters we have considered here. One is small tk, that means how long it is above the level of Vt. This is one parameter. And also we have considered that what is the gap between the crossovers. So this capital T is the gap between two consecutive crossovers when only the noise signal itself is there. Okay. So from here, we can write the expression of the false alarm probability or false alarm time. This is false alarm, not probability. This is false alarm time. There is gap between these two consecutive threshold for only the noise signals. So that we are writing with the help of this one. Okay. So from this time graph, can we rewrite the expression of the PFA? Let me include here. Can we write this PFA? How we can write this? What is the probability of the false alarm then? What is that? It is the ratio of the envelope when it is actually above this one to the total time what it is available to us. Isn't it? So actually for the ticket duration, small ticket duration, it is above the threshold. So what is the probability of this thing? Probability of these things we can write in this way. Summation over k is equal to 1 to n That means let us consider the phenomena is appearing for n times. So if we take sum of all these durations, that means here it becomes above the Vt for the small tk duration. Again here we are getting the thing is above the Vt for the small tk duration. Again here. So let us take sum of all this time. That means when it is really above the Vt. So if we take all these things, this is the sum divided by the total time it may be. So total time it may be means the gap between all this. So for this we can write this is as k is equal to 1 to n sum of capital Tk. Okay. So if I just ornament both of them with 1 by n and limit n tends to infinity, then this entire thing is what? This entire thing is small tk average divided by this thing is nothing but your TFA. So this is your TFA. Clear? Is it clear? So just if I rewrite the equations, then we can write this PFA as in the denominator it is false alarm time, and the numerator it was just simply like this TK average. So TK average, that is the actually, if I consider that what is TK average is actually, this time is actually the inverse of the bandwidth. From where it is coming? Let us go back to our receiver subsections. The portions where we are considering these things, these portions, isn't it? After the IF amplifier, the second detector and video amplifier. After the IF amplifier, whatever the signals we are receiving, that is the radar bandwidth operations. And the bandwidth of this thing is, we can write as B. Because after this, the thing is processed across the second detector. So second detector may be an amplitude detector or it may be a phase detector. Here for the profile of R, purely it is an amplitude detector. You know there are two kinds of amplitude detector. Either it is based on the square law device or it is based on simply the linear range of the diode. And usually, if we consider for the normal operations, that is when there is no signal, just to calibrate the receiver itself, if we use the linear range, then the same bandwidth is operated here. So when it is giving some existence of the signal, so that means it is purely indicating that time is responsible for this bandwidth. Clear? So when we are considering this Tk, that this T is responsible or this Tk is what? This Tk is the time duration when the signal is above the threshold. So this T is nothing but the processed B, inverse of the processed B. So instead of these things, we can consider this as 1 by P into TFA. Okay. So this is the equations or this is the interrelationship of the false alarm probability with the false alarm time and B. And I think the previous expressions where it was in terms of the minus Vt square by 2 psi naught, instead of that, this expression is more user friendly, isn't it? And even we can write it is in terms of false alarm time only, that is TFA is equal to 1 by B into PFA is equal to 1 by B. PFA means this one. So this is exponential. That minus will be in the numerator. So this divided by 2 psi naught. Now look at the expressions. This expression is much more friendly. And this gives us a pure, clarification that the ratio of the Vt and psi naught, what are they? This Vt and psi naught is Vt is your threshold, decision threshold, and psi naught is your root mean square noise level. So the ratio of these two, how uh, clearly we are maintaining the, or how correctly we are maintaining to maintain the ratio of this Vt and psi naught, that becomes totally responsible to control your false alarm probability or to measure the gap between this false alarm probability in terms of the time scale. Okay, so this is a measurement. And for example, just if we take a numeric value for this, that means if we take that if B is equal to 1 megahertz, suppose the radar is operating over this 1 megahertz bandwidth, and the false alarm timing that is a 15-minute. That means at every 15 minutes we are led by a false alarm buzzer or the kind of that things. Then the calculation of these things give us that the this false alarm probability, I mean this PFA calculation of this TFA, if we substitute TFA is 15 minutes, B is 1 megahertz, then PFA value we will get in terms of 1.11 10 to the power minus 9. Okay, and from here the threshold voltage, if we calculate the threshold voltage, that is the VT square by psi naught, this value will be 16.2 dB. Okay, so if we are able to maintain the VT square by psi naught at the 16.2 dB, then for 1 megahertz, the false alarm time is 15 minutes. Okay, and there is a very beautiful graph interlinking all these things from where we can get a set of data that what are the relationship of this one. So this is your VT square by 2 psi naught that measured in dB scale, and this one is the average TFA. And let us consider that things we are measured in hour. Okay, these are the things. Let us take 3 or 4 divisions over this. So the ratio, if we measure it in terms of hour, then it is 1, 0.1, 1, 10, 100, like this. Okay, and correspondingly, if we map this in terms of scale, then this is your 1 hour scale. And as this is started from 0.1 hour, so suppose here the intermediate value is for 15 minutes. Okay, 1 hour, then it is here will be 12 hour, then here it will be above this, it will be 1 week, and then month in terms of year, like this. If we extend the graph from 100 to here up to more multiples of 10, that is 1000, 10,000, like this, it will go even up to the year. Okay, so with this one, if I just plot the things for the different bandwidth, then this is the graph. In the here also let us maintain the level. Starting level is 10, 9, 10, 11, 12, 13, 14, 15, 16. Already we have seen a data that when this VT square by psi naught is 16.2, then your PFA is of this value, T main is of this 15 minutes. So these are the things. And for the different bandwidth operations, if I plot this, then when the bandwidth is of value very less, 10 hertz, and this is for the higher bandwidth, even for 1 gigahertz. This is for 1 gigahertz. In the intermediate values, there are different values are there. That's it. That is of the 100 megahertz. This 11 is for 1 kilohertz. So what the graph actually explains, these lines are the operated bandwidth. So here the bandwidth, operated bandwidth is 1 gigahertz. Here this line is 100 megahertz, and this line is the most little bandwidth, that is of 10 hertz. And here in the on the horizontal scale, the thing is the ratio of the decision threshold and the RMS noise power. So where the graph is touching, that means 12 dB, 11 dB, or in between 9 and 10 dB, at 14 dB, here it is near to 15 dB. So these are the giving us the corresponding ratio between these two and the chances of the false alarm timing. Okay, because here the things we have plotted in terms of hour, starting from 0.1 hour, it can extend up to 10,000 hour or like this. So the corresponding mapping even go for the year also. So just if I look to this year, then what is the maintained level of this one? Based on that things, we can get a value of the corresponding chances of the false alarm timing. Whatever the examples we have considered here, that kind of measurement is already available in the graph. So considering from the graph, you can get an idea that what operated bandwidth, what will be the expected VT by 2 sign up, so that we can expect the false alarm time at a gap of 1 hour, at a gap of 12 hour, or weekly or yearly like this. Okay. So these things is giving us and clear pictures of the false alarm probability or the false alarm event. Now, just the opposite event of this one is the misdetections, because this false alarm probability or this problem is or this issue is that when we are getting the fluctuations for the noise itself. Now the thing is, when both the signal and noise is there, but the fluctuation is not enough to cross the level of the VT, then what happens? Okay, so based on this one, we will consider the probability of the detections. So let us come to the probability of the detection. So when we are considering the probability of the detection, then first thing we have to consider an echo signal as a sine wave of amplitude A along with Gaussian noise at the input of envelope detector. Okay. So usually the things what from where we are taking the, although the entire receiver chain is very high, because prior to IF amplifier the match filter is there. Prior to that one, a low noise amplifier is there. One stage mixer circuit is there, but we are not taking the entire one because entire one is not. If we take entire one, the calculations will be much more complicated. So let us consider only the crucial part. That is from where we are just taking the voltage trace or the phase trace of the received signal or the actual signal. So what we have considered? We have considered suppose a real amplitude, that means an amplitude which is arising from an object that is showing with the notation A, that thing is present along with the noise itself or along with the clutter itself. And when it is processed across the envelope detector, then what are the chances of the detections? Okay, so usually the envelope voltage, what we have shown it with the help of R. Okay, so the thing we have written in terms of some probability density function. So as it is related with the signal detection, so let us indicate notation that is P suffix S function of R. So that is equal to what? That is equal to R by psi naught exponential. In the factor, what are the voltage? Instead of R only writing only, we have to write the existence of the A also. And how they are? All of them are superimposed condition. So what we can write? We can write for this one as R square plus A square divided by 2 psi naught into this by psi naught. Okay, what is this? This is actually RA psi naught. Let us consider this is as Z. So this I0 Z is the modified Bessel function of zero order argument Z or RA by psi naught. Okay. So now let us clear, make it clear that what is this? This R is the noise envelope. So within the not only the noise envelope, this is the signal envelope, what we are getting across the second detector. Okay. So when the signal also present across the Gaussian noise or across that kind of things, then the thing we are writing as if the existence of A, that is extra attachment over the profile of R. So because of these extra additions, usually we are getting the frequent exceeding of the signal voltage over the Vt, and that is in favor of the probability of the detections. So the function is getting modified in terms of minus r square plus a square by 2 psi naught, and whole thing is multiplied by these Bessel functions. Why this is a Bessel function? Because if we follow the nature of the scattering cross section, which is really responsible from some new object or the appearing object, then that thing is a kind of distributions like this. Because based on the nature of the object may be still object, the object may be a moving object. So whatever the kind of object or whatever its nature, based on these things, actually the echo collected from this new sigma, that is in terms of this decaying function. And if we map this function, that matches with the Bessel. Because for the Bessel functions, what we get? We get a decaying sinusoidal functions like this, overlapping decaying sinusoidal function. So the uh, existence of the A, that things we can consider in this way, the whole noise envelope that is modified by this extra current, what I have shown with this I naught function of RA by psi naught. So that is nothing by this Bessel one. Okay, clear? So that is why the PDF, that is the probability density function, that is get multiplied by this Bessel functions or this kind of things. So this is valid only when the thing is where the echo from the object that becomes very prominent, and that creating a contributions over this one, and the existence of that thing is there. Okay. So what is the probability? This is the PDF. So what is the probability of the detection? Probability of the detection. To get the probability of the detection, we have to integrate this density function within the proper limit. So for the probability of the detection, this is as the capital P. Let us indicate as PD. This is equal to integration Vt to infinite Ts. S means some real signal is there. So that is why we are writing every times this into dr. So whatever the expression of this one, that is the mathematical expression of this one, this I0 is giving us a Bessel kind of function as per the contributions what we get from sigma, and this is multiplied by this profile. This is a very complicated functions. So we are not able to integrate these functions under these integrations. So we have to go through numerical and empirical method. We have to go through numerical analysis and empirical. By numerical analysis, we can get a chain of the synthesis from where we can get some best fitting formulas. And by using the empirical means, just by taking the data and taking the matching of this mathematical formula, so that which formula will be fitted for the data that we will pick up as our solutions. So that is known as the empirical method. So if we go both the numerical and the empirical method, then we get a kind of best fitting formula which is available for the detection theory. And usually we find the detection theory or the detection formula in terms of the signal to noise ratio. So before that, let us signify the things. That thing is, here one thing is there, exponential minus r square plus a square by 2 psi naught. So let us indicate that what is that? R by psi naught, That is when we will integrate this over this one, then usually instead of r, what we write Vt square by psi naught. So that gives us a kind of, uh, threshold voltage to noise, RMS noise ratio. So when we do this for A, then what does actually it means? Because inside this Bessel function, there is also RA by psi naught. Okay. So let us first indicate that what this A by psi naught actually means. So if I write this, that is A by psi naught root. This one is how much? Or this one is what actually this says us? This A is what? This A is signal amplitudes. Because look at here. Here we have considered the echo signal of amplitude A. So A is nothing but the signal amplitudes. And this psi naught is the RMS noise voltage. Okay. So if I consider this is as the signal amplitude, then can we express it in terms of the signal power? Yes, we can consider it is in terms of the signal power, root of signal power, and this is your noise power. This is your noise power. This is already in root form. And when we relate amplitude and the signal, this will be in also root form. So this whole thing is whole to the power half. So we can write, if I adjust the RMS factor, that is root 2 factor here, then that entire things can be considered as
Yeah, actually.
2s by n whole to the power half. So actually A by root psi naught, that things we can write in terms of 2s by n whole to the power half. These two factors we are getting because of the RMS factor. So now
চার্জ দিয়েছো?
let us move to the next one. So this probability of detection, this P by D, that can be PD, that can be written in terms of this Vt square by psi naught, or the in terms of this signal to this one. So just if we go for the result only, that is after fitting the empirical formula, we are getting a very good relationship. So here we did not impose the whole solution method, just we are writing the formula in the ready-made way. That thing is S by N is equal to A plus 0.12 AB plus 1.7 B. What is your AB? A is equal to ln 0.62 divided by PFA, and B is equal to ln PD divided by 1 minus PD. Okay. So how do this come? Because a relationship of PFA is simply Vt square by 2 psi naught. And for the A, what we have obtained, the formula for PD in terms of S by N. So just if we fit it for the output formula in terms of S by N, because usually the demand of S by N, that what is the relationship between the S by N, so that we can get the proper detection, that is led by this formula, and this is known as the Albertson formula. This is known as Albertson formula. Okay. So if we take a example of this one, that means to run this one, if we consider that PFA, PFA is ranging between 10 to the power minus 3 to 10 to the power minus 7. Suppose you are taking the PFA value starting from 10 to the power minus 3 to 10 to the power minus 7. PD value, that is a probability of detection, is from 0.1 to 0.9. Okay, correspondingly these values. Then we can obtain a value of the S by N for this. That means to specify the problem with this PFA for the probability of detection, if like this, and if we consider the bandwidth is again for the 1 megahertz, then we can obtain the related S by N for this one. and the S by N will give us a value for the, we'll have to 14 to 15 dB, 14.9 to 15 dB. Okay. So if we maintain the S by N ratio as near to 15 dB, we get the value of this one is, if this is 10 to the power minus 7, then we get the probability of detection of like this. If this is of 10 to the power minus 3, the detection will be with the probability of the 0.1. Okay. So this gives us a ratio of the kind of things. So this is a very important things regarding the probability of the false alarm and the probability of detections. Another thing is, and this obviously happen that based on a single observations or the single data, we are not able to justify this. For this, we need the multiple observations or the multiple data. Only based on the multiple data or the multiple observations, we are able to give some detections theory or the detection criteria. Now, another thing is parameter is integration of pulses. Integration of pulses. Okay. What is the integration of pulses? Because already when we have studied this one, this gives us a clear picture that based on a single data, it is not possible. For this, we need the multiple data. Then only the theory of the Salvation that can give us a strong criteria for the probability of the detections or the proper data for the detections. Okay. So to do these things, we need the multiple time of pulses. And how do we can sum up all these multiple pulses? That is known as the integration of pulses. Clear? Integration means taking the sum of over all the individuals. And why it becomes necessary? It becomes necessary to get a proper conclusions, because it may happen that the fluctuation is only for the noise, or it may happen also that there is some modulating current from the real target or the real object, and because of that things we are getting the conditions. And just if we have a loop over this S by N, inside the S by N, both the contribution of probability of the false alarm is there and both the probability of the detection is there. So that means these two are simultaneous. Probability of the false alarm is also simultaneous with PD and the vice versa. So no one is absolute, that only the false alarm is absolute there. No, the PD probability of detection is absolute there. Actually, both are simultaneous. So with the respect of both the events, we have to find what is the S by N, or what will be the proper difference between the threshold Vt and the psi naught. That we have to decide very crucially. So to do that, we have to integrate the pulses. That means we have to take the sum of different pulses at a time. So this process is known as the integration, and this process is of two kinds. One is known as the pre-detection, another is one is known as the pre-detection, another is known as the post-detection. Okay, and the classification, pre-detection as the post-detection, that is based on where is the location of the integrator. The sum up procedure is after the second detector or before the second detector. If it is before the second detector, then it is known as the pre-detection. If it is after the second detector, then it is known as the post-detection. Both the processes have some advantages and disadvantages. If it is pre-detections, that means if it is prior to the second detector, then all the phases of echo should be reserved, should be reserved. Because if we lose the phase information, we will lose the Doppler informations. Later, I will show you that the Doppler frequency of the Doppler information that we have obtained from the phase of the echo signals. So not only the amplitude, both the phase and amplitude that should be reserved. So that will be the nature of the integrator if it is pre-integrator. If it is post-integrator, then already the kind of detector is defined. because that may be only amplitude detector, that may be only phase detector, that may be both amplitude and phase detector. So already the conclusion from the amplitude or the phase, that information is already extracted. So no need to carry the phase informations. So only if we take the sum of the pulses, we are able to do the integrations. So that is your post integrations. Okay, clear. So now how do we do the integrations, or what is the formula for the integrations? So the formula for integration is, suppose we are integrating n number of pulses, that means n number of observations. Clear. So n is the number of pulses, that is number of observations. So that is equal to how much? That is equal to bandwidth of the antenna used, pulse repetition frequency divided by scanning rate. So if I state it in terms of theoretical statement, then the thing is number of pulse returned from a point target by a scanning radar with a pulse repetition rate of 80 hertz, antenna bandwidth 3b degree, 3b degree is equal to, with the scanning rate theta is dot is equal to like this. So this is how much number of pulses received by a scanning radar. Because if scanning procedure is not there, then you will not get the multiple data. Scanning procedure are different kind of procedures. Later we will show it in terms of in the chapter of the scanning radar. So that means repetitive observations. Okay, repetitive times we are taking the data from the different directions. This theta b is the bandwidth. So scanning radar with the rate what gap these things will come at a pulse repetition frequency fp and with antenna theta b. So theta b is the interaction area. The rate of the scanning is theta is degree per second, and rate of PRF, that means at what rate this beam will appear, that value is 80. So if these are the specifications of the scanner, then the number of pulse what we obtained, number of pulses are integrated there, that value is equal to S by N, which is obtained with single observations by N. Okay, so what is the factor? This is also S by N, this is also S by N. This S by N is when we are taking a single observations. This S by N is also data for single observation, but that we have obtained after N integrations. So just if I look to this, so this is equal to N times of this. Okay, so obviously we are getting an improvement factor. That factor is known as the N factor, and the efficiency ratio for the numerical measurement. This is the efficiency ratio, that is equal to S by N, that is signal to noise ratio for the single observations, S by N. This is also signal to noise ratio for the single measurement, but n pulses when are integrated, this thing is like this. Okay, so this is known as the efficiency. And we can also measure the corresponding loss, because when we introduce some device there, so the loss of that things that will also be included into the total factor. So loss of the device also we can obtain by taking the reverse of this. That things also we have, I have shown you that the gain of lossy device, how we have performed this 10 log 10 base 1 by attenuation. So here also we can find the loss of this integrator, that things in terms of 10 log 10 base 1 by this EIN. Okay. So these are, it becomes important for to find your small numericals or the kind of these things. Now the two portions are there. That is the, if we go back to the mother equations here, escaping all these things, a very important thing is sigma. That is the scattering cross section. And to model the sigma, and it is not a very simple thing. Actually, to model sigma, there are multiple models are there. Okay, and it is not very. It actually the contribution of this sigma is not very direct also, because if we think about a flying aircraft, then with which portions the radar incident energy is interacting with the this flying aircraft, or what is the kind nature of the flying, whether it is a kind of whirling movement or it is in some these directions. That means with which area of the aircraft we are getting the intersections of the energy. Based on that things, we are getting the nature of the ego. If it happens with only the nose of the aircraft, then it just we are getting a reflections, or we are getting a scattering cross section only from the tip of a metallic ball. The whole length or the whole object will not be projected there. If we get the interaction or the interceptions from the wings or from those kind of things, then the interceptions will be something different. There will be some decaying type of wave like this, because the operating wavelength, there the factor will appear that what is the operating wavelength and what is the length of this panel. So comparing these things, there are different type of scattering techniques: Rayleigh scattering, Mie scattering, optical scattering. So at which zone it will belong, based on that things we will get a view like this. Okay, so never we get a clear picture view of the total aircraft. Actually, based on the interception area and the interception directions, we are getting a projected view. And from the projected view, we have to map this for the actual geometrical figure. So the role of sigma is very important. And never, suppose if we get it from a flying bird, so based on the nature of the feather, we will get a very weak echo signals. And not only that, where from which portions of the bird we are getting the generated echo, that is whether it's from beak portion or tail portion or it belly portion, from where we are getting the echo. Based on these things, we are getting a projected view. And sum up, taking all the projected view, we can get a picture that may be a figure like this, from where we are getting this sigma contributions. So modeling of sigma is a very crucial factor. And if we go only through the modeling of sigma, a book can be written over that. It is so vast and so large. So just here we will not go into the so much details of that things. Just keep in mind that this role of the sigma, and uh, how do we can make this sigma for the sufficient to get the established for the probability of the detections. Okay, so that is the things. So if we go for the entire estimations of the range equations or the minimum power detections, then all the factors becomes responsible. The last one is the G or the AE. That means what type of antenna gain or what types of antenna aperture. So usually that is the what type of antenna gain or the antenna aperture we use the large antenna aperture, and sometimes based on the nature of the operation, that if it is a scanning type of operations or those kind of operations, sometimes it is replaced by the scanning type of radar, that is electronically steerable antenna, where we can use the phased array kind of technology to get the quicker scannings or the quicker kind of methods like that. So that we will consider when we will consider the system itself or the device itself. Okay. So up to this, the first portion or the first part that is covered. After this, we will go into the system-wise descriptions. So for the system-wise description, first descriptions we will go for MTI radar, that is the moving target integrator or pulse Doppler radar. So today I will not start the discussions of the things. Just let us have an introductions over this MTI and pulse Doppler. We are using two titles here because both of the MTI and the pulse Doppler radar, they are based on Doppler operation or the Doppler principle. Full form of MTI is moving target indicator, moving target indication. Okay. Pulse Doppler is also used to indicate the movement. So that means when your target or the object is a moving one, then with the range we have to also specify that what is the velocity of the target or object, what is the acceleration, what is the directions. These things are also becomes very important for the moving target indication. Okay, so for the MTI and pulse Doppler, actually one is range unambiguous, one is Doppler unambiguous. That means one radar, one class MTI and pulse Doppler, one class acts over the unambiguous ranging and the other class. For the MTI class, they use very low PRF. They use very low PRF. If we use the PRF very low, PRF means pulse repetition frequency, isn't it? That is at what gap the pulsatings are there. So this low PRF are used to get what? To get unambiguous ranging. Unambiguous ranging. Because we have to be very specific about the appearing range, not about the moving characteristics of the object. Is it clear? The basic operations of radar is range. Now, when range is covered, then we go for the second or the third or the fourth kind of conclusions. So the next conclusions are about the when the range is there. Next conclusion is about the location. That means the angle parameter. At what angles they are appearing. Next, what may be that at what velocity. If it is a moving, then what velocity it is moving. Then the direction. At what direction it is moving. It is approaching towards you or going away from you. Then the thing is what is the acceleration of the things, etc., etc. So the degree of the things that go on increasing based on the demand. But both these two radar use the Doppler event. But when we use the Doppler event, we have to be very specific that whether we are interested to find the Doppler event, that means the dynamic feature of the target or the appearing range of the target. If we are very much cautious about the appearing range of the target, that means we do not bother about the dynamic feature of the target, just we want to detect that at that range whether there is any target or not, then we will use the moving target indicator. For the moving target indicator, pulse repetition frequency is very low. So that means at long gap, the pulse repetition frequency is there so that we want to avoid any multiple around echo. Okay, because we have to be very cautious that all the echo for the first pulses, they will be collected, then the second pulse will be transmitted. The gap is so long. Clear? So it is for the unambiguous ranging. That means about the range or about the distance, we should be error free. Then we use the low PRF. If we use the high PRF, if we use the high PRF, that means we transmit the pulse with low gap. Then your ranging will not be very pure. Why? Because then you will not be able to identify that the echo what you are collecting, that was the delayed echo for the first pulse or the first echo of the second pulse. Similarly, delayed echo for the second pulse or the early echo from the third pulse. Clear? If it is delayed echo, then obviously it is coming from a long distance. If it is early echo, so that means it is coming from a near object. So from this operation, you are not very uh, fixed about the appearing range. So range information is not very correct from the high repetition or the high pulse repetition frequency. But what will be useful there? The Doppler event. That means when the object is moving, at what velocity it is moving, that feature, dynamic feature of the object, that factor can be extracted very nicely if we use the high PRF. Okay, so these are the two basic classification between the MTI radar and the pulse Doppler radar. So in the next class, first we will define that what is your Doppler principle. From there, how we are able to find normally the Doppler velocity or the kind of things, and then we will go for both the MTI and the pulse Doppler radar with the schematic and with their limitations, with their advantage. Many more things are there. Okay, so system-wise descriptions we will start from the next class. So now please let me be clear that what are the things, because the detection theory what we have considered, that theory is not very simple theory, and as it is a elective paper, so obviously the thing is in a very high end, so that things we have to take along with us as the paper is with us. And here the things what we have considered, actually there are different detection theory. So excluding all of them, just simply the formula or the numerical part, what is responsible, what will be responsible, we have taken out only, or we have sought out only those things and have given the considerations. Okay. So regarding these things, you just read out the things. If you can go through the books also, you read those things, and if any small numericals or the MCQ type of questions that may be from there, so please go through the materials or go through the matter, then at least you will have some idea or the criteria. Okay. So any questions or doubt? I think lots of doubts are there, but you are not expressing. You can feel free to ask any doubt. Okay. Let us leave the class.